Hello everyone, and welcome back to a new episode of SHENZHEN I. That last episode went a bit longer than I realized that it had, but you know what? We got it done. It was less than an hour. All in all, a success. I suspect it won't be too long before we start getting to puzzles that we can't do in a single reasonable length episode, so we'll probably start splitting them up. Oh well. What are we up to now? Is this our congratulations for the last thing? Working remotely, yeah, okay, right, the traffic jam, I remember. Okay. Where's this? Looks like an actual design and create an electronic game. Oh my gosh, we're game designers. Alright, does this say anything like super interesting? I don't know. Let's just get started. Wait, click and hold this button to indicate that I have completed the objective. What? Wait, did the solitaire one have the same thing? No. I don't understand. We can test with different things. Prototyping area. Okay. So it looks like this is maybe just a sandbox area where we can just play around with whatever we want. A bunch of parts that we don't even know what they are yet. We could look them up in the manual, but okay, we don't really want to do this. We want to do the next puzzle. A virtual reality buzzer. Goodness gracious, there's a lot of text there. Okay, so this radio has a non-blocking X-bus buffer. Oh no! It returns -999 when no data is available. That seems so much worse than a blocking one. So I guess that's the challenge here. Let's figure out how to deal with shitty parts. Alright, so what do we have to do? Radio-RX, that's this one, receive, get a non-blocking X-bus input. Buzzer is a simple output, that's this one. When a data packet is received, read it and execute the corresponding command in the following table. So we'll read something and it'll either be 0, 1, or -999. Okay. That doesn't seem too bad, honestly. We just need the one X input port and the one simple I/O port. I keep X input. Cannot keep straight the word X bus. It's just not possible. So we're gonna have to read the thing, compare it to 1, compare it to 0, and that's it. Otherwise, wait, so that's weird. Since we can't count on the radio to like provide us a source of time at all, we're just going to be treating it like a simple I/O, right? We're going to check the value, do whatever with it, and then sleep 1. Huh. All right. Well, here we go. Get a chip. Wire this guy to here. This guy to here. And we are just going to test equal x0 with 0. If so, we are going to move, if it's 0, turn the buzzer off, move 0 to P1. Otherwise, we'll start another test, And so here's a little interesting trick that I thought of. We'll see if this works. But the idea is we could do something like jump init or whatever here, assuming we wrote an init label. But that's an extra instruction to execute, more power probably. So what I was thinking is, instead, we put a minus instruction here to only run a test if the corresponding thing, if it's possible for the test to succeed, right? And we just have to make sure to write the test such that it only executes in minus mode, right? So if we don't run this test because the previous thing was set, then we don't want to accidentally like do anything in here. So we want to make sure that plus is the neutral don't do anything result of this test. So what test can we write where a neutral result is don't do anything? We could test whether the value is... Wait, does this thing output minus? What is this part? Let's actually... I know it was in the instructions for this level, but let's see if we can find it in here. Are there... I read that there are like bookmarks in this thing. I don't know. Non-blocking buffer. Yeah, that's this one. It yields minus 999. Okay. So it seems like, well, actually, do we have any examples where the input is something other than 0 or 1 or minus 999? It doesn't look like it. So what I would like to do then is just compare against minus 999. Test equal x0 with minus... Wait a minute. Ha. I can't actually keep comparing against x0 because each time I read, I'll be using up a value. So I have to actually start by moving x0 to ACK. Why did my M not appear? And then test ACK here in both of these. Compare against minus 999. Now, if it was minus 999, I shouldn't do anything. But if it wasn't minus 999, I should move as a 100 to P1. Next, in either case, I should sleep for 1 unit to get to the next input, right? This looks pretty good to me. So we read a thing and it was minus 999, so we tested it at 0, no. Now we'll test it's minus 999, it was, so we don't do that move, and we sleep for 1. Likewise, now, we've moved this to ACK. There's a 1. Is it 0? No. Is it minus 999? No. So we move 100. Turning on the thing. Alright, that looks good to me. Nope, it didn't turn off. Stop. Oh, it's supposed to blink when it's on. What? Where did I read that? It's a buzzer. I see. So if the buzzer is on, Alright, I need to be a little bit more careful here, I guess. Let's look at this again. What are we supposed to do? So while the buzzer is on, I need it to oscillate. Ideally, I'd like to do that without any branches. So that I don't have to mess with the existing structure. All right, so let's just confirm that what we have now is, yeah, it's correct insofar as like when it's supposed to be doing something, it's doing something, but it's doing the wrong thing because it's not oscillating. Right? Yeah. Alright. So that means the 0 case is already correct. The only issue is what we need to do in the 1 case. So we can't just move 100 to P1. But what we can do instead seems relatively straightforward, I think. We will just move P1 to ACK, call not, and then move ACK to P1. Oops, let's put a minus on here, please. Right, so the idea is, okay, we've determined that we are in a state where we want to oscillate, so read the current value into ACK, negate it, and write it out. So let's see what happens now. We move P1 to ACK, so we now have a 0. We negate it, we write that to P1. Great. Now, again... Oh, no! Okay, so this is wrong. Because we have to do that when it's minus 999, not when it's 1. Right? This is a little trickier than it looked. We can't just, when the thing is on, a minus 999 needs to toggle it, right? But when it's off, a minus 999 needs to do nothing. Write a 0, right? Okay. Isn't there like... There's some simple logical function that... probably like an XOR or something, right? No. So the output written to P1... I can't quite see a place where we can save the state that we need, right? We could almost save it in x0. Like if we only had to read x0 a single time, then we could store our state about where we are in ACK. But we can't do that because in order to use the same value from x0 twice, we need to read it somewhere else. Now, I read an interesting suggestion online when I was trying to look up how to delete wires, which is that you can use a pin that you don't care about as just a place to store state. Use it as an extra register, basically. So that's an interesting idea. We sort of gain a register this way if we can figure out a thing to do with it. We could probably also solve the problem by grabbing one of these guys. I don't know how to turn off Steam notifications. Maybe I should figure that out, huh? I can like go on, whatever, it doesn't matter. There's literally only one person on my Steam friend list who ever like pops up with activities, so sorry about that. If Sorry, mostly to him, not to you guys, that he's getting into the Steam name public in the videos, but you know, please leave him alone. Alright, so we can do, this has a register we explicitly can use to do nonsense with. But I think we only need one, so we can use a pin. The question is, can we fit all this in the small number of lines of code we have? Maybe. So my thinking is, we'll use P0 as the state of, like, is the buzzer currently in on mode? And then we'll basically say, we'll write to P1 the result of knotting the old value and ANDing that with P0, so that we only actually write something if we only turn it on if the buzzer's in on mode. Okay, so the thing is, though, I'm not sure we can fit that in 9 lines. We're gonna have to move x0, I guess, into ACK, since we can't afford to overwrite anything else. We could maybe write it to, no, yeah, we can only write it to ACK, okay. Then we're gonna test whether it's 0. And if so, write a 0 to both of my pins. Actually, I can write a 0 only to this on pin here. Otherwise, do this test, and if it fails, then move a 100 to P0 here. And then in either case, so we've gotten to, like, here basically, right? In either case, we will next do what? Call we will load up P1 into ACK, then we'll knot it, then we will AND that with P0. Alright, so what I think is that we're 1 instruction short. So let's write it on one of these guys. Okay. And actually, why are these two connected? What? Get out of here. We want to read from x0 here, so I guess we'll do it like that. And now we're going to do basically much of the same stuff that was over here, but I'll retype it in because I'm not sure. Oh, and we don't need this P0 anymore either, because we have an actual register designed for holding stupid nonsense like this. So, fine. We're going to move x0 into ACK. Test whether ACK is 0. If it is, we'll move a 0 into our DAT register here. Otherwise, we'll test whether ACK is minus 999. And if it wasn't, then it must have been 1. Therefore, we'll move a 100 into DAT. Next, what we will do is move P1 into ACK, knot it, AND it with dat. What? Didn't we have an AND instruction? No? Okay, well that kind of sucks. What are DGT though and DST? DGT. Digit, right. I remember now. So digit get and digit set, basically. We don't have an AND. Okay. That stinks. Well, do I really have to do this by hand? You have to do everything by hand in this damn game. I mean, you can write arbitrarily complicated Boolean expressions with just like jump if greater than, but boy does it suck. We don't exactly have a lot of space to work with. So, what exactly do we do here? So instead of moving P1 into ACK and trying to do this with Booleans, let's do the following. Let us now compare whether or not the thing is on. Yeah. Okay, so what we'll do is we will test eq dat of 0. If it is 0, then move 0 to the output. Otherwise, move its old state into ACK. Not that. Move ACK. I've got to negate it. Move ACK into P1. In either case, we now sleep 1. So am I correct that, yeah, we ended up using 11 instructions, so it's not clear that we could have done this in 9. So let's see what happens. This can be removed. Okay, so now we move x0 into ACK. It's 1. We test whether ACK is 0. It's not. We test whether it's minus 999. Again, it is not. So we move 100 into dat, saying the alarm is now on. And now we test whether that was 0. Well, it's not. So we move the old state of P1 into ACK, and it's 0. We negate that, and we move it back out, and it's 100. Okay. Now we're gonna read x0 again. We get minus 999, nothing's happening. Is it 0? No. Is it minus 999? Yes. So don't change the onness variable, but just test whether it's off. It's not off. So now we move the old thing in, flip it. Uh-oh. What happened there? It stayed on. Why? This thing's wired up to P1. Step, step, step. We test whether dat is 0. It's not. We move P1 into ACK. It's 0. Why is it 0? Shouldn't it be 100? Can't we read our pin? What's going on here? That's P1. In previous exercises, I thought we had been able to read what our output pin was. Right? Didn't we have, Let's go back and look at a previous one where we did some oscillation. Like there was that drinking one, right? Light up signs. Pulse generator actually is even a better example. We moved. Wait. We checked whether P0 was 100. Step. It was not. Oh, P0 is the input. Oh, we never actually read our pin here. We left the state in ACK. Alright. Do we have an example of where we actually did do that? What about this? I thought we had done it. Then he moves from a pin. Not in this puzzle. Interesting. This one, right? Every time this puzzle gets worse. When I learn the dumb ways we're constrained. I mean, and that's the point of games like this, is to constrain you, so you have to think at really low levels of abstraction rather than high that we're sort of used to these days. So, what am I supposed to do if I can't read that pin? Also, I read people saying that you can, so I'm a little confused. Do I need another chip to hold this state? That kind of sucks. I don't see where we have room for any more state to be held if we can't put it on the pin. I can't believe we don't have AND. That sucks. Test equal, greater, less, compare. Maybe we could do a weird compare to get us sort of an AND. Oh, but we can't even read what was there. Gosh. Well, it's starting to seem like no single chip design can work. what two chips would we split it up into? We could have a chip that's responsible for... Well, I was thinking it could be responsible for, like, providing an actual clock, but... we kind of need one chip that stores in its accumulator the current state of the register, of the buzzer. Not whether it's on or not, but whether it's currently, like, actually high, making noise. And give that guy like an X input telling it to, or an X bus input telling it to flip or something. But it's a little bit hard, like telling it to flip versus to become inactive. It seems like this one shouldn't be so hard, but it doesn't have a lot of tools. And I can't figure out what the right way to split this up is. I don't know, is this music distracting me? We'll see. I'll try taking off my headphones and see if I think better that way. So there's sort of like 3 different tasks going on, right? One task is that of determining whether the buzzer should be on right now. One task is oscillating if it is on. I feel like that first task might actually be 2, right? Determining if it should be on right now. Okay, so it sort of seems like what this big old chip is doing right now is the correct way of handling what it's doing in DAT, i.e. storing whether the buzzer is on. That's a useful thing for a chip to do. And I can just send that as a direct, simple input into another chip, which checks that every cycle and basically acts like the pulse generator, right? We already wrote pulse generator. We know we can do that. And we just want its input to be something derived from this chip here, rather than a basic input. So we could actually even go grab our code from that other guy. But it means we're not going to need, I think, quite as much code here, and we don't need the DAT register either, right? We can, in fact, like, remove these 3 lines, because the whole point is only to output stuff to P1, not to DAT at all. So P1 1. And then we can just remove all these lines, right? Now all we're doing is reading the input into the accumulator, check if it's 0, and then check if it's minus 99. Okay, so this is all a very simple job that we can squeeze onto one of these guys easily. Throw this away. Throw all the wires away for the moment. This guy wants to give us X input, so we'll just wire it up like that. And we even wrote P1 here, how nice. Although actually, maybe P0 would be better. Right, and then we'll just take this, feed it as an input to another one of these guys, and let's write this from scratch, I guess. We could go copy it from the pulse generator, but it's so easy and it's good to practice, I guess. So what we're going to do is test whether P0 is 100. If it is not, then we need to move 0 into ACK. Otherwise, we need to not the result of ACK here, because that means the buzzer is on. In either case, we now move ACK to P1 and sleep for a turn. So I thought I did this in 4 cycles before. Am I wrong? No, it was 5. All right. So, stepping. Okay, we sent it this. Oh, interesting. It's out of phase, huh? Okay. So we need this sleep 1 to be at the beginning here to make sure that the other guy has time to send us our input before we... why is it a line drawn? There we go. We want to make sure this chip does all its work for the cycle before this chip does any of its work. So this guy sleeps at the end, this guy sleeps at the beginning. Fine. This is not actually working. That's interesting. Why is this not working? And it was working before. I guess they both wake up from their sleep at the same time. So I could add a few knops, I guess. That's a little sad. To make sure, we need to give this guy room to do at least 1, 2, 3, 4 instructions before we even start looking at stuff, huh? So this is actually starting its cycle just after receiving the first input. Well, okay, first of all, that means it's wrong, because if the buzzer had been on in the very beginning, we should have been making noise, and we're not. So we can't put a sleep 1 at the beginning. That's not helping things at all. we need to put it at the end. And we, it seems like, need to put nop, 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 nop here. Yuck. And now, yeah, we're sort of semi-correctly doing stuff. And we get here just in time to test the thing, and we turn on the buzzer. Okay. The buzzer. Now we could have afforded to be faster in this case because no changes were being written. But okay, we waited long enough. We tested whether it's on. It is. So we just negate the accumulator and write it out. All right, I'm reasonably happy with this. This looks all right. Woo, go fast. Yeah, I don't know. These graphs suggest that they're like measuring tests that I ran, even though those tests didn't pass, which is not useful at all. I don't need to know how cheaply I could build the wrong thing. Well, back to the email. How did we do? That was exactly as I imagined it. Cool. And feel the connection and get ahead. Are you lonely? Do you feel isolated and disconnected? Scientists have shown lack of all this stuff can lead to depression, which is bad for you at work. Don't let the lack of human interaction reduce your effectiveness. Virtual friends are virtually indistinguishable from real life people. Okay, so buy a virtual friend, apparently. So that was plenty of time for a single episode, I suspect, although I have not looked at the timer. At any rate, we're not starting a new one now. So thanks for watching, and I'll see you next time.